The truth about black holes. They're not all the same. Mind-blowing types you didn't know. Hello, cosmic explorers, and welcome to Cosmic Enigma. Today we're diving deep into one of the universe's most mysterious and misunderstood phenomena. Imagine a black hole. What comes to mind? A cosmic vacuum cleaner, perhaps? A singularity devouring everything in its path? Most people picture one terrifying, all-consuming entity. But what if that common image is one of the biggest misconceptions in astrophysics? The truth is, our universe is home to a fascinating family of these gravitational giants, each with its own incredible story and unique role. Today, we're going to meet them all. Before we dive into their diversity, let's quickly define what a black hole actually is. At its core, a black hole is a region of space-time where gravity is so incredibly strong that nothing, not even light, can escape. This extreme gravity is caused by an immense amount of matter packed into an incredibly small space. The boundary beyond which escape is impossible is called the event horizon. Think of it as a one-way door to the universe's most extreme environment. Once you cross it, there's no coming back. It's not a hole in the traditional sense, but rather an object with such immense density that it deforms space-time itself. Despite their name, they don't suck things in like a vacuum cleaner. Their gravitational pull works just like any other massive object, only far more intensely at close range. If our sun were replaced by a black hole of the same mass, Earth and other planets would continue to orbit it exactly as they do now, just a lot colder. For a long time, and still for many today, the image of a black hole is singular, a dark, mysterious void. This leads to the common misconception that all black holes are essentially the same size or type. However, astronomical observations and theoretical physics tell a different story. Black holes are actually categorized into several distinct types, primarily based on their mass and how they form. This classification reveals a universe far more complex and intriguing than a single, monolithic black hole concept. Understanding this diversity is crucial because it sheds light on stellar evolution, galaxy formation, and even the very early universe. Each type represents a unique cosmic process. Black hole classification is primarily based on their mass, with four main types recognized by astronomers: stellar mass, intermediate mass, supermassive, and primordial. The most common type of black hole in our universe are stellar mass black holes. These cosmic behemoths are born from the dramatic death of massive stars. When a star, typically more than 20 times the mass of our sun, exhausts its nuclear fuel, its core collapses inward, triggering a catastrophic supernova explosion. If the remaining core is dense enough, more than about 3 times the sun's mass, it continues to collapse beyond a neutron star, forming a black hole. They can also form from the merger of 2 neutron stars. Stellar mass black holes typically range from about 3 to 50 times the mass of our sun. They are incredibly dense, with an event horizon only a few tens of kilometers across. Imagine a black hole with the mass of our sun, but only 6 kilometers wide. Our Milky Way galaxy is thought to harbor as many as 100 million of these. We often detect them in binary systems, where they pull material from a companion star, heating it up and causing it to emit bright X-rays. These black holes are almost always spinning due to the conservation of angular momentum from their progenitor stars and typically have zero net electric charge. Their formation is relatively well understood, representing the natural endpoint of the life cycle of massive stars. Next, we have the most mysterious and elusive members of the black hole family, intermediate mass black holes, IMBHs. These are the missing links, bridging the gap between stellar mass and supermassive black holes. Their masses typically fall between 100 and 100,000 times the mass of our sun. The biggest puzzle surrounding IMBHs is their formation. They are too massive to form from the collapse of a single star, and their environments lack the extreme conditions seen at galactic centers that give rise to supermassive black holes. Current theories suggest 2 main formation scenarios. First, through the merging of multiple stellar mass black holes and other compact objects. Second, through runaway collisions of massive stars in incredibly dense stellar clusters, like globular clusters. These collisions could form a supermassive star that then collapses into an IMBH. Detecting IMBHs is incredibly challenging, which explains their rarity in observations. Globular clusters, with their tens of thousands to millions of stars tightly bound by gravity, are considered prime hunting grounds for these elusive objects. Observatories like the Hubble Space Telescope play a crucial role by observing the subtle gravitational effects these black holes might have on surrounding stars. Recent gravitational wave detections, such as GW 190521, which resulted in a 142 solar mass black hole, provide compelling evidence for black hole mergers creating objects in this mass range. The ongoing search for IMBHs is a major area of research, as understanding their formation could unlock secrets about how the universe's largest black holes came to be. At the other end of the spectrum are the true monsters of the universe, supermassive black holes, SMBHs. These colossal objects reside at the very heart of nearly every large galaxy, including our own Milky Way. Their masses are truly mind-boggling, ranging from hundreds of thousands to billions of times the mass of our Sun. Our Milky Way's central black hole, Sagittarius A star, pronounced A star, weighs about 4 million times the Sun's mass. But that's relatively modest compared to others like the one in galaxy M87, famously imaged by the Event Horizon Telescope, which clocks in at over 6 billion solar masses. These black holes can be incredibly luminous, especially when actively feeding on gas and dust, forming quasars that can outshine entire galaxies and be seen from billions of light-years away. While we know SMBHs grow by accreting matter, eating stars and gas clouds, and by merging with other black holes during galactic collisions, their initial formation remains a significant mystery. Observations show that some SMBHs formed surprisingly early, within the first billion years after the Big Bang. Theories suggest they might have started from the collapse of massive stars in the early universe, or even directly from the collapse of enormous gas clouds. The direct detection of gravitational waves from merging black holes has opened new avenues for understanding how these giants grow and evolve. The relationship between SMBHs and their host galaxies is profound. They appear to have grown together over billions of years, strongly suggesting a co-evolutionary birth. Finally, we venture into the realm of the hypothetical. Primordial black holes, PBHs. These are not formed from dying stars, but are theorized to have originated in the first fractions of a second after the Big Bang. In that incredibly dense and hot early universe, tiny fluctuations in density could have caused pockets of matter to collapse directly into black holes, without the need for a supernova. PBHs could theoretically have a vast range of masses, from incredibly tiny, less than a paperclip, to thousands of times the mass of the Sun. The smallest ones would have evaporated by now due to Hawking radiation, a theoretical leak of energy from black holes. However, larger primordial black holes could still exist today, and some scientists even propose them as a candidate for dark matter, the mysterious substance making up most of the universe's mass. While definitive proof of their existence remains elusive, the search for primordial black holes is an active area of research, especially with the advent of gravitational wave astronomy, which might one day detect their subtle signatures. While mass is the primary way astronomers classify black holes, there's a deeper, more fundamental way physicists categorize them: by their observable properties. According to the no-hair theorem, a fascinating concept in general relativity, an isolated black hole can be completely described by just 3 external measurable properties: its overall mass, its overall electric charge, and its overall spinning rate, or angular momentum. This means that once matter falls into a black hole, most of its unique characteristics are forgotten or smoothed out, leaving behind only these fundamental quantities. For instance, there's no such thing as a rocky black hole or gaseous black hole, like there are rocky planets or gaseous planets. All the matter that falls in gets crushed down to an indistinguishable clump or ring. These 3 properties, mass, charge, and spin are conserved and affect space-time curvature, making them externally measurable. In our universe, most black holes are expected to be spinning because they form from spinning stellar remnants or accreting material. They also tend to have zero net electric charge, as any charge would quickly be neutralized by attracting opposite charges from their surroundings. Therefore, while theoretically possible, black holes with significant electric charge are considered rare or non-existent in practice. Beyond the single-type misconception, black holes are often surrounded by other popular myths. Let's clarify a few more. First, despite their name, black holes aren't entirely black in the sense of being completely invisible. While light can't escape from within the event horizon, we can detect light near it, especially from the superheated gas in their accretion disks. The Event Horizon Telescope's images are prime examples of this. Second, the common fear that if you get within a few thousand miles of a black hole, its supergravity will pull you in is not entirely accurate. You can actually get surprisingly close to a black hole without being pulled in, as long as you're outside its event horizon. If our sun were replaced by a black hole of the same mass, Earth would continue its orbit undisturbed. The gravitational pull at a distance is the same as any other object of that mass. Only when you cross the event horizon or get spaghettified by extreme tidal forces near smaller black holes does escape become impossible. Third, while it was long believed that once inside a black hole, nothing ever comes out, Stephen Hawking's groundbreaking theory of Hawking radiation suggests otherwise. Quantum mechanics predicts that black holes slowly leak radiation over vast timescales, eventually causing them to evaporate. This isn't matter escaping, but rather a quantum effect at the event horizon, fundamentally changing our understanding of black holes as truly inescapable entities. These clarifications highlight how our scientific understanding of black holes has evolved, moving beyond simplistic notions to a more nuanced and complex reality. So the next time you hear about a black hole, remember, there isn't just one kind. From the stellar remnants born of dying stars to the enigmatic intermediate mass black holes, the colossal supermassive giants at galactic cores, and even the hypothetical primordial black holes from the dawn of time, our universe is filled with a rich diversity of these gravitational marvels. Each type offers a unique window into the extreme physics of the cosmos and the incredible processes that shape our universe. Science is an ongoing journey of discovery, constantly refining our understanding. Black holes, once thought to be uniform cosmic vacuum cleaners, are now seen as a diverse family, each playing a crucial role in the grand cosmic tapestry. If this journey into the diverse world of black holes expanded your mind, please consider giving this video a like and sharing it with fellow cosmic explorers. Don't forget to subscribe to our channel for more deep dives into the universe's most fascinating phenomena. And tell us in the comments below, which type of black hole do you find most intriguing? Or what other cosmic mysteries would you like us to unravel next?